Hello there, this is a geometry video. It is chapter 7, section 4, and today we will be discussing parallel lines and proportional parts. And so we have our first theorem, the triangle proportionality theorem, and it basically states that if a line is parallel to one side of a triangle as BE is parallel to CD, and if that line also intersects the other two sides, AC, so it intersects here at B, it intersects AD here at E, then it divides, it being the segment, divides those two sides, AC and AD, into segments of proportional length. So we know that AB is to BC as AE is to ED, and that's what we have here in the black. It says if BE is parallel to CD, then AB to BC will equal AE to ED. So we're going to use that theorem. If we can get my pen to function here. Oh, there it goes. In this first example, it says in triangle PQR, ST is parallel to RQ, and if PT is 7.5 and TQ is 3, so remember we said that if that happens, if they're parallel, then it divides the sides proportionally. So we know that PT is to TQ as PS, which is what we're being asked to find. We don't know what PS is to SR, which is 2.5 according to the given information. So we just set up a proportion like that, and then we go ahead and solve for PS. So we know 3 times PS will equal 7.5 times 2.5, and we're going to get out our trusty calculator here to calculate 7.5 times 2.5, which will give us 18.75. Then we divide both sides by 3, and we find out that PS is actually equivalent to 6.25. And just like that, we have answered example 1. So now if you will go ahead and use the same diagram but with different information here for do-it-yourself number 1, we will go on to our next theorem, which is basically the converse of what we just discussed. So the converse states that if a line intersects two sides of a triangle, so again in this case we have ED as a line that is intersecting both sides of the triangle, and separates the side into proportional corresponding segments, then the line is parallel to the third side of the triangle. So basically if the proportion is right, if AE is to EB as CD is to DB, then AC is parallel to ED. So we have the converse of the triangle proportionality theorem. So now we're going to apply that theorem to example 2. In triangle DEF, EH equals 3. So we're going to fill in some of that. EH equals 3. HF equals 9. So the ratio of EH to HF is 3 to 9, which is equivalent to 1/3. And then we have DG is 1/3 the length of GF. So if DG is 1/3 the length of GF, we don't actually know the exact length, but we know that the ratio is 1/3 as well because it says that DG is 1/3 the length of GF. So one way of looking at it is if you go ahead and call DGX, then it means that if DG is 1/3 the length of GF, it means that GF is 3 times X. That's basically what that means. And so again, if you were to set up the proportion of X to 3X, the X's would cancel and you would get 1/3. So we have equivalent ratios of 1/3 there. So because the segment divides the sides proportionally, then that means that DE is in fact parallel to GH according to the converse of the triangle proportionality theorem. Now we're going to give you some different information for do-it-yourself number 2, same diagram, but this time DG is half the length of GF, and then it has different different lengths, for EH and HF. And so again, it's asking the question, with this new given information, will DE be parallel to GH? That's up to you to figure out. So then we go to our next theorem, and that is the midsegment theorem. And I want to remind you, if you have forgotten, that the midsegment of a triangle is the segment whose endpoints are midpoints of two of the sides. So this would be considered a midsegment because K is the midpoint of HG and J is the midpoint of HF. I know that because it's marked congruent, so J is in the middle, congruent, so K is in the middle. So just want to remind you, if you had forgotten what a midsegment was, it's a segment with endpoints that are the midpoints of two sides of the triangle. So of course, every triangle will have 3 midsegments, but here specifically, we are going to deal with one of them so that we can just make this theorem a little bit more straightforward. And it says, a midsegment of a triangle is 2 things. It is parallel to one side of the triangle, and its length is 1/2 the length of that side. So again, that might sound a little bit confusing to you. So over here, again, we have it pretty much written out in more concrete terms. It says if J and K are midpoints of FH and GH, so we already said that FH, J is the midpoint because they're both marked congruent here, and K is the midpoint of GH for the same reason. So if that's the case, then JK, which is the midsegment, is parallel to FG, so it's parallel to the third side. That's the first thing that the theorem tells us. And also JK is half of FG. Okay, that also means that that FG is double JK. It's another way of looking at it, okay? So we're going to use that theorem here. In this example, it says in the figure that's on the board here, we have XY and XZ are midsegments. Okay, so they're telling us that they're midsegments of triangle RST, and they want us to find each measure. We're going to start with XZ. So here's XZ, and what we know is that RT is 13. So since RT is 13, RT is double XZ, or so to speak, XZ is half of RT. Again, this is the midsegment. It's going to be parallel to RT, and it's going to be half the length of 13. So basically, XZ is equal to half the length of RT, or half the length of 13, because that's what RT is equal to. So then basically, we're going to get 6.5 for XZ. So XZ equals 6.5. And then we're going to move on to ST. And ST is a little bit backwards because now, like I said before, XY is the midsegment. So XY is half of ST, which means that ST is twice XY. So ST is going to equal twice XY. And XY is actually 7. So that means that ST will equal 14. So ST equals 14. And then we have the last one here, the measurement of angle RYX. So RYX is this angle right here. And since we know that these XZ and RT are parallel because it's the midsegment, so it's these two are parallel, and this is basically a transversal. So I just kind of want to reemphasize here, we've got 2 parallel lines cut by a transversal. And so what we have here is that angle RYX ends up being an alternate interior angle with YXZ, which we know is 124. So that means that the alternate interior angles are congruent. So angle RYX is also equal to 124 degrees because it is an alternate interior angle with the other YXZ angle. So we have now done all of that example. So now we'll give you a different diagram and ask you to find these measures before we move on to our next theorem. All right. So now we have the proportional parts of parallel lines. Corollaries. So our next 2 theorems are actually corollaries, and if you remember, corollaries are one-line proofs that we can add to an existing proof and get our next theorem. So it's not a very long proof, it's kind of just an attachment of an already existing proof. So this is our first corollary, proportional parts of parallel lines. And so basically it's extending it to not just the triangle, but 3 or more parallel lines. So basically it says if 3 or more parallel lines intersect 2 transversals, okay, then they cut off the transversals proportionally. And again, that might sound kind of confusing, so we have over here written out in a more concrete way. If AE, so here's AE, parallel to BF, and then also parallel to CG, if all three of those lines are parallel, and it could be more than that, then the segments of the transversals are going to be cut off proportionally. So basically we're going to have that the ratio of AB to BC is going to equal the ratio of EF to FG. So we're not saying that AB is equal to BC, we're just saying that there's a ratio, and the ratio of these two segments will be the same. All right, so we're going to use that corollary to do this example here. And this is actually a very simplified version of the example in the book. The example in the book states that Megan is drawing a hallway in one-point perspective. She uses the guidelines shown. So basically all I've drawn in the diagram are the guidelines. If you actually look in the book, there's a lot more to see. But the AX here and the DY here, these two segments, are the guidelines that she's using to draw windows on the left wall. And so basically the bottom line is these are the windows. Here's a window here, and there's a window there. So it says if segments AD, so here's AD, BC, WZ, and XY are all parallel. Furthermore, we know that AB is 8, and DC is 9, and ZY is 5. They want us to find WX. All right? So what we know is that because these are all parallel, and there's more than 3 lines there, it could be 3 or more. We have 4 lines that are parallel. It tells us that it's going to divide the segment lengths proportionally. So basically means that 8 is to WX, which we don't know yet, as 9 is to 5. So we just set the proportion. 9 times WX will equal 8 times 5, which is 40. Divide by 9, and WX equals 49ths, or approximately 4.4 repeating. And that's in centimeters. All right, so that's basically how you can apply that corollary to this problem. So now again, we're going to give you a do-it-yourself question. Again, I did not write the entire question out for you, but basically the book states that frontage, so the word here that we're using, frontage, is a measurement of a property's boundary that runs along the side of a particular feature, such as a street, lake, ocean, or river. And in this case, it's an ocean. Again, if you look at the diagram in the book, we have a big ocean over here on the side. And then we've got basically a road, which is right over here. And I only wrote down in the diagram the parts that were crucial. So it says, find the ocean frontage for lot A. So we know that the ocean frontage for lot B is 60. Basically, the distance between here and here is 60. This is the property lot B, so its ocean frontage. How much of it is facing the ocean is basically here to here, 60. So it's asking us to find the ocean frontage. So what I did is I added X. So basically what they want us to do is find X. And X goes from here to here. It's the ocean frontage of lot A to the nearest tenth of a yard. But basically all you have to do is set the proportion, and then you can figure that little guy out. So then we have one last corollary, and it is the congruent parts of parallel lines, unlike the previous one, which was proportional parts. Now we're talking about congruent parts. So it's very similar theorem or corollary, but not the exact same thing. So this time it says, if 3 or more parallel lines cut off congruent segments, so this time they're not proportional segments, they're actually congruent segments, which they have marked here, on one transversal, then that means that it also cuts off congruent segments on the other transversal. So basically, if AE is parallel to BF and in turn parallel to CG, and you also know that AB is congruent to BC, then that means that EF must also be congruent to FG. Now, we're not saying that the segments will be equal to each other, but these two segments will be equal to each other. So now we're going to go to our last example, and then we will call it a day. All right, so it tells us here to find X and Y, so we have a diagram, and this time we know that not only are all the segments parallel, but these two segments are marked congruent, and they want us to find x and y. So the easiest thing to do right now is probably to find x and y, because we know that these two segments have to be the same. So we're going to go ahead and solve for y first, because we know that 3y plus 8 has to equal 5y minus 7. So then we're going to subtract 3y from both sides and get 8 equals 2y minus 7. Then we're going to add 7 to both sides, and that'll give us 2y equals 15. Divide by dose, and y will equal 7.5. And they didn't give us any units, so there's your y value. Y is going to equal 7.5. And then we want to do the same thing pretty much for x, because again, since we know that these two are congruent, then it must be that these two segments are congruent because of the congruent parts of parallel lines corollary. So we know that 6x minus 5 must equal 4x plus 3. So we subtract 4x from both sides. That gives us 2x minus 5 equals 3. We add 5 to both sides. So 2x will equal 8. And then we divide by 2. And finally we get that x equals 4. So our y value was 7.5. And our x value is going to be 4. Based on the congruent parts of parallel lines, corollary. So now we will have you do these two examples as part of do-it-yourself number 5, solving for x in each case. And so good luck to you. Once you have completed this example, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.